Hi kids, it should be Friday. It should be Friday the 19th, and this is our lesson for today, and I've tried to tag it from the previous days. It should be day 2. So this is going to encompass the rest of 15.1 and going to add all the way up to 15.3. So there's like parts kind of going in and out. But I've got some homework for you here. I know it looks like a whole lot, but I'm going to do a couple of the problems along the way, and they're not really that many problems. I think like 7 problems total. But you can, it won't be too bad. So it's really like 5. But here it is, page 656 through page 657, 21 and 22, 25 through 28, and then 31 and 32. So I'm going to start off with number 31 right now, and then we'll just kind of get through, and we'll try to work through all the way through so that we can get you some work done today. All right. So here is 15.31, and I will like shoot on over to the book just to show you here. Here it is. It says here methanol is produced commercially by a catalyzed reaction of carbon monoxide and hydrogen. Here's the reaction. At equilibrium, the mixture in a 2-liter vessel is found to contain 0.0406 methanol, 0.170 mole carbon monoxide, and 0.302 moles of hydrogen at 500 Kelvin. Calculate the rate constant, K, C, at this temperature. So I'm just going to run through this problem, and you can read through it. If you have your book, you can open it up and kind of go along. I'm going to write it all out, everything that I have. So here we go. So I start off with this. I wrote out all the variables, what we're looking for. We have here 2 liters, and then here's Kc. At equilibrium, it said I had 0.17 moles of carbon monoxide, 0.302 moles of hydrogen, and 0.0406 moles of methanol. So all I'm going to do here to find the concentration, remember we need a concentration, which is moles per liter, and I'm going to change all of these to a molarity. So I divide by the volume given. They're all in that container, and so you divide it all by 2 because of the container size. So here's what I got. Here are my concentrations. Let me zoom in a little bit here. Yeah, here are my concentrations of each species, and I tried to line them up, try to keep them all in line for you. So this is methanol, hydrogen, and carbon monoxide. All right, so now that I have my equilibrium concentrations, I can fit them into my expression. So I can generate my expression. Let me put this here. There it is. Oops. So there's my expression, and it has methanol, which is the products, over the reactants. And notice I do not forget the coefficients become the exponents. Then I can plug in my values that I got. So 0.0203 molar, and then 0.085 molar, and 0.151, and I'm going to square it. Make sure you be careful on this one here. So I wrote it all out, and it looks like this. These are the values here after you square it, and then you solve it, you end up getting 10.5. Oh, excuse me. There you go. 10.47, you round up 10.5 for 3 significant digits. And that's the answer. It's unitless. Those rate constants become unitless. All right, so that tells me that it favors the products, it favors the right. And just to kind of give you a little hint, that's what we were working on yesterday. All right, so for today's stuff, here's what we got going on. So we're going to be working with this new rate constant. It's called Kp, and it's equilibrium constant for pressure. Very similar. It's actually the same thing except a couple little twists. And I'm going to go way back to our ideal gas law. PV equals nRT. And if I would divide by V, it gives me this. And remember, moles over volume, this is a molarity. That's a concentration. And if you go through and you perform the equilibrium expression, you can actually get Kc. Kc is going to be from the equilibrium expression, very similar to what we did up there. Make a long story short, here I put it in here. This is a concentration, so it's concentration of whatever we're dealing with times RT. So this here, the proof for this next statement is right here. So on page 628, it goes through this proof, but right now I'm just going to kind of trust me on this, because what it does is it takes this Kc value, so if you can imagine the products over reactants, that's what goes on here, and that's what's generated from this particular reaction. You can go through it. But it ends up here with this Kp, and here's the relationship between Kc and Kp. Kc times RT. R is your rate, your gas law constant, that R constant, and then here's T. Now this is a delta N, and I wrote out a little spot here for delta N. Delta N is the moles of the product minus the moles of the reactant. So just for example, we go all the way back up here to the methanol one. There's 1 mole here. So then for this guy here, and I can put it right here just for example, we're not going to use this one here, but nonetheless. So the only product I have is methanol, so it'd be 1 minus, and then I would add up the total moles. There's 2 hydrogen and 1 carbon monoxide, so 3. So then my delta N would be a minus 2. So that would be an example how to solve for delta N. But here it is. So we're just going to kind of keep this in mind, and I'm going to kind of breeze on through, not to kind of wash over it or glaze over it, but we're going to use this expression, and we're going to do a couple problems, and you got a couple homework problems on it too, so I'll use it right now. So this is from the book. There's a sample example 15.2, and it's again the Haber process, and here it is. N2 nitrogen plus hydrogen gives me ammonia. So here we go. So I wrote out all the things that I know. Here it is. It gave me in the problem this Kc value, 9.6 at 300 degrees Celsius. I need to change this to Kelvin, and then I have my Kp value. There's a couple things here. I wrote out some stuff here. I'm going to use this R value of 0.08206 because the pressures that we're dealing with in this problem are atmospheres. We're going to convert to Kelvin, and it tells me that it's in a liter, and that's the particular units that they're using. So I kind of keep all the units together. I take 300 degrees Celsius, convert it to Kelvin. I've taken the liberty of solving for delta N right over here. So notice I take the 2 from ammonia, and I'm going to subtract the combination of 3 and 1, which is 2 minus 4, which gives me a negative 2. So when I perform my expression, that's where my minus 2 is going to come from. And here it is. Here's my expression, and let me write it all out for you. There we go. So here's my Kp is equal to my Kc that was given to me in the problem, 9.6. And then here's my R value. And then the units get all canceled out. Like I said, make sure they just line up with what we're using. And this one here does talk about atmospheres. So if it was kilopascals, you could use 8.314. But this one here uses atmospheres in the Kc value, where we originally got this value from. So that's where we use it. Excuse me, not where we got the Kc from. Sorry about that. But the atmospheres that were in the problem. And so you make sure you are choosing the right one. This is the typical one we're going to use for gases when we are using atmospheres, just to give you a heads up. And then here's where I put the delta N. So I must perform this mathematical operation first, multiply it, and then I'm going to square it because it ends up in the denominator. That's what this negative does. Puts in the denominator, and then I can square it, and I take 9.6 divided by this giant denominator, and I get a 0.00434. This is the value for my Kp. And that's the relationship between Kc and Kp. Not real complex, not real hard, but that's just what we're going to do with our problem. So you will have some problems that will ask you to solve for Kp, and when you do have a Kc, and then vice versa. We'll do a sample problem in a moment here. In fact, yeah, we're going to do it right now. So let's try this one here. This is one of your problems here on the homework. This is the second one here. This is 15.33, so this is number 33 in your homework, and it tells you this here. Well, let me show you in the textbook so you can see it. Right here. The equilibrium of 2NO plus chlorine yields 2NOCl. It's established at 500 Kelvin. An equilibrium mixture of 3 gases has partial pressures. Here they are. So it'll give you the atmospheres, and so I know I use the right R value based on the atmospheres. And so it says here 0.095, 0.171, and 0.028 atmosphere, respectively, for NOCl2 and NOCl2. So here's the 2 questions. The first one here is calculate the Kp for this reaction at 500. And then the second one we'll get here in just a second. It says if the vessel has a volume of 5 liters, calculate Kc. Don't let this throw you off. We're just solving for Kc, and we know the relationship between Kp and Kc. Oops. All right. So here I've written out the equation, and I've written down the concentrations or the pressures, the partial pressures at equilibrium. Now I could treat it the exact same way I did the concentrations, and that's why I did that one first. So it says here Kp at 500 Kelvin, and that's what I'm solving for. So on this guy here, when I go and I solve this, let me show you the expression here without getting you too cluttered up with all this other stuff. Here it is. So take a look. I have my products over my reactants. I set it up exactly the same as if it were a Kc, but on this one here, I'm using partial pressures. I have my products over my reactants right here. Don't forget to square these. Now I can plug in my partial pressures, and notice that these are the atmospheres, 0.028, 0.095, and 0.171, and then they're squared. So you just do the math, get the math going, and you just solve for Kp. And there it is. So it has two significant digits. 51 is my answer, and that's what I'll stick it. And then it's just that simple. So when you have something that's Kp, you're going to be using the partial pressures. Kc is going to be using the concentrations, just to kind of differentiate between the two, just so that you know. So then the second part here was wanted to solve for a Kc value, and it gives you a volume of 5 liters. Don't get tricked by this, but you can use it. That justifies our R value as well. So here's the relationship. Kp is equal to Kc RT to the delta N. I solve for my delta N, and it's 2 minus 3 is equal to -1. If you're not sure, go up here. Here's 2 from the products. I'm going to combine these two. 2 plus 1 is 3, so it's 2 minus 3. That's where the minus 3 came from, and it gives us a -1. So that's what my delta N becomes, and it looks like this. This is a -1, and it immediately moves it into the denominator, and you can see, oh yeah, I can solve for Kc. All I'm going to do is I'm going to take RT and multiply it on both sides. So it looks like this, and it frees up my Kc. And so now I have Kc is equal to Kp times RT, and I set up my expression. I get this 51 from the problem above. That was part A. That was my Kp value. Here's my R value, 0.08206. Remember, I'm using atmospheres, liters, and I have everything else mole and Kelvin, and this will actually cancel out with it. And I left with a unitless Kp value. That's what this becomes. This is my my Kc value from my Kp. It's 2.1 times 10 to the -3. So that's just a quick little rundown. They're not like tremendously difficult, but again, it's just a little relationship between concentrations and partial pressures, solved both ways using the equilibrium expression. So don't forget your homework tonight. This will be due on Monday. Here it is. Sorry about that. It'll be due on Monday. I hope you all have a nice weekend. We will be going over this material on Monday and taking it a step further. All right. Take care, kids. Have a great one.